Okay, Planck's constant is one of the fundamental constants of nature. There are only 7 of them. And so to be able to measure it in the classroom with just a little box with some LEDs mounted in it is actually pretty impressive. We're going to enjoy ourselves measuring this constant. So how are we going to do it? Okay, so what we've got here is a circuit that just basically connects a power pack to the LEDs, but it's via this potential divider or variable resistor, which just means that I've got a dial that I can change the potential difference with. To be honest, I don't really need it because I've got one on the front of the power pack, but never mind, we'll do the one on the kit. I've got a selector here which can pick the different LEDs. And I've got a voltmeter attached here, which is just going to tell us the potential difference across the LED. I'm going to have the room, that's a bit bright, isn't it? I'm going to have the room pretty dark to see the LEDs. So I'll just turn the lamp on and off as we need it. You are actually going to kind of help me to do the measurements, although it's going to be, well, we'll see how we go. So how's this going to work? Last lesson, we spoke about the photoelectric effect, which was where a photon released an electron and the electron came out with some kinetic energy. Well, this LED is a semiconductor device. And what's actually going to happen is that there are a pair of electrodes inside the LED, and we're going to make an electron jump across the gap. It's going to jump from the one electrode to the other electrode, crossing the gap. And when it arrives at the second electrode, it's going to dump its energy, and that energy is going to be converted into a photon. So it's a little bit, slightly, a little bit conceptually like the photoelectric effect backwards. Rather than a photon releasing an electron, we're going to use an electron to release a photon. The principle is the same. The LED has been engineered using the right chemical composition of the materials the electrodes are made out of and the correct gap of the electrodes. The LED has been manufactured so that when the electron arrives, it is only capable of falling into a particular energy slot, energy level in the lattice that it's about to arrive in. So it's only if the electron arrives with the right amount of energy that it will be allowed access to the other side of the gap. It's only then that it will be allowed to cross the gap. And what that means is that I will need to change the potential difference here gradually up and up and up and up and up until the power supply is providing the electrons with enough energy. Remember, potential difference is measured in joules per coulomb, and an electron has got a certain amount of coulombs. So I'm going to use the power supply to provide the electron with just the right number of joules so that it's capable of crossing the gap. So I can just demonstrate that really simply now. So if I turn the power pack on and the potential divider is down on 0, I've got the selector on the red LED. So you can see that if I just turn it right up, turn on the power pack first. If I just turn it right up, oh no, it's a blue LED. The light comes on at some point, and it gets brighter and brighter and brighter because it's releasing more and more and more photons. However, you'll notice that if I turn it down so that it's off, the voltmeter is still reading a value there, despite the fact that the LED is not releasing any photons. And that's because up to this value here, I am not providing the electrons with enough energy to release any photons. Remember, it can't release any old photons of any size because the LED has been manufactured to only release photons of a certain size And therefore, unless the electrons come in with at least that energy, it can't release those photons. So what I'm looking for here is to find the threshold at which the potential difference is just big enough to release a photon. That's what I'm looking for here. So this is called the threshold potential difference. It's the potential difference at which it is possible to start releasing photons. Now, at the moment, this value is way too high, and that's because I've got all the lights on in this room. And in actual fact, that LED is releasing some light. It's just we can't tell, we can't see it because it's too bright in this room. So what I need to do is turn off all the lights in this room and allow the camera, which is actually working much better than my own eyes. I practiced this earlier. We need to let the camera pick up the very first flickers of photons that start coming out. And then we turn the light back on and see what the voltmeter reads. And it'll be lower than 2.45. We're then going to do that for each of the LEDs and work out what the threshold potential difference is for each sized photon. Now, why are all the photons different sizes? Well, that's because all these LEDs are different colors. So there's a dark blue one to go with the kind of lighter blue one. And then we've got, again, can't see it so well in the light, but there's a green one. And then we've got a red one as well, and then a deeper red one. These two are actually in the ultraviolet. No, the infrared. Yeah, that's right. They're in the infrared, and we can't see them. So that's actually on. Both of them are on. Actually, that one's being picked up by the camera. That's quite cool, isn't it? But we'll have a go with that one. But the others, all different colors. And remember, Einstein claimed that the photon energy is related to the frequency. In actual fact, this experiment's always done in terms of wavelength rather than frequency. But we know how to convert from our waves topic that we've done. So these are all the different wavelengths of the photons that are coming out, and therefore we can convert that into different energies. What we're then going to do is try to compare the energy from the voltmeter to the wavelength of the photon using Einstein's equation, well, Planck's equation, and this will allow us to dig a value of h out of the data. So we'll do the experiment first, and then I'll switch the camera back to the board at the front of the room and we'll do our analysis of it. So what you need is a table of results that has 2 columns initially, but we are going to add some other columns to it. So make sure there's some space to add more columns. But 2 columns initially, one for wavelength and one for threshold PD. The wavelength is measured in nanometers, nm. And the threshold PD is measured in volts, V. Your values for the wavelength are printed on the box that you can see in the video. So just copy those down into your table. But we aren't going to do the 875 one. I wasn't going to do the 950 one either, but it did just flicker on the camera then. It's possible that this visualizer's camera can pick up that wavelength. It might even pick up the 875 one in the dark. We'll have a look. I didn't try earlier. Okay, so you should have written down 430, 505, 560, 615, 655, 875, possibly, and 950. Okay, let's have a go at this then. So I'm going to turn the lamp off and it's going to go pretty dark in here. And then in the midst of all that darkness, you are just looking for a little bit of light coming out of that LED. Okay, let's see how this works. Okay, so I'm just going to turn it back down just a little bit. Really hard to get it exactly right. That's still on, isn't it?
Yeah.
I'm too far away from my monitor to see it
I
properly.
think right now is like the limit.
Yeah?
Yeah, that's pretty good.
Okay, let's have a little look at that then. So that's coming in at 2.24. So if you scribble down 2.24 as your threshold PD for the 430 nanometers. Okay, let's switch it to the next one and have a go. Cables are in the way. Okay, so 2.24, that one's already on. So just turn it down a bit. It's still on a little bit, isn't it? All right, let's go there. Okay, so that one's coming in at 2.09. Maybe 2.1. Or 2.09, make up your mind. 2.09, let's go with that. And that was for the 505. Have a look at the 560. Might turn that ever so slightly too far. It's not actually very easy to turn the dial. It doesn't turn in tiny little increments. Okay, what about that? That's just gone out. Oh, it's not going to make up its mind. Come on, stabilize. Bouncing around all over the place at the moment. Okay, there we go, 2.03. And that was for the 560. Oh no, I haven't moved the dial. Okay, that's a repeat reading of these other LED. This is why you guys should be here. You're better at experimenting than I am. Okay, 2.10 as a repeat reading for the second LED. You can average the two values if you wish to. All right, let's go up one to the green one. We'll try that one again, 560.
Wait, so it's the same one?
No, this is 560 now. I just did, I told you the last one was 560, but I accidentally forgot to move the dial. So in actual fact, I did a repeat of the 505 one. You know, because doing repeats is good technique, right? Okay, so this is the next one, the 560, and this is the green one, and we'll just turn that down just a little bit. Okay, I think it's around about there. I've moved about the width of a hair, so let's go with that. So that's the 560, and that's coming in at 1.53. Try the 615 now. Change the dial. Okay, let's have a go at the red one. Ooh, that's quick. Right, should we go with that? When you're doing this with your eyes, you have to allow your eyes to adjust to the dark, which is then really annoying when you have to read the voltmeter. We tend to get people kind of hiding under their blazers with a voltmeter and a torch while their mate does the experiment. Okay, so the red one, 615 nanometers, is coming in at 1.48. Let's try the 655 one now. Have a look at that. Okay. It must be around about there somewhere. Again, I hardly moved it then. Okay, so 1.32, 1.31, 1.31. That's for the 655 one. All right, well, let's see what the camera can pick up for the other two LEDs. Not convinced that's picking up anything. Try the other one. That LED's just burnt out. So just for the record, I can't see a thing coming out of that LED with my eyes. It's just completely black to me, even though it's up maximum. But the camera's obviously picking it up. I actually wonder if the LED's burnt out for that second one, because if the camera can pick up this one, there's no reason it wouldn't be able to pick up the other one. Okay, joy of cameras. Right, let's turn that down a little bit. Just about on, isn't it? Okay, let's go with that. I know it's just about on, but I'm not sure I can move it any less. Okay, so value for that's coming in at 0.95. All right then, so let's have a little think about what we're going to analyze here. So what's going on is that we've got some energy from the electron crossing the gap in the LED. Is being used to create a photon that has a certain frequency. So this is the equation E equals HF, but we've got that, actually I'll write that a little bit like that. We've got this bit is HF, and this bit, well, the voltmeter is reading the potential difference, which is joules per coulomb. That's the V bit. So if we just want to convert the joules per coulomb into joules, we need to know how many coulombs an electron has got. Because if the voltmeter is reading 0.95, that means it's 0.95 joules for every single coulomb. Does anybody remember how many coulombs an electron has got?
Is it 1.6 times 10 to the minus 19? Or is that the other way around?
No, that's correct. And we usually represent that algebraically by E, which stands for not the electron charge, but the elementary charge. The elementary charge. And technically there's a minus sign on that, but we're not really interested in whether we've got positive or negative charge. We're merely interested in the amount of charge. Our data doesn't have a frequency in it. Do you know an equation from your waves topic that converts frequency into wavelength?
Speed over frequency.
Yes, speed over frequency. Oh, it's wavelength. Okay, so wavelength is, yeah, the other way. So this is the wave equation. Speed, in this case, the speed of light, equals frequency times wavelength. So frequency is equal to c over lambda, and we can put that in there. And that means that we end up with this equation. I'm just going to divide through by the E. V equals HC over E times lambda. No, lambda's on the bottom. 1 over lambda. Now, it's a slightly clunky way of writing the formula, isn't it? So why have I written it like that? Well, I've written it like that because we could just take each of our data points and just sub them into the equation on our calculator and get a value for H out. But that's not the way that we usually handle data. A great averaging technique is to draw a graph, and the line of best fit averages out all of the random errors for us. So we are going to draw a graph of one lot of data against the other lot of data. So we've got the wavelength, which is our independent variable, and we've got our potential difference, which was our dependent variable. And we could just draw a graph that looks like that. But the prediction from our theorizing is that V will be, this is just a load of numbers. That's just a number, that's just a number, that's just a number, that's just a load of numbers. When we multiply it together, it's just a number. So let's not worry about that. We've got V will give a graph of 1 over lambda. So when lambda is very, very small, V will be big. And when lambda is very big, V will be small. And in fact, the graph is going to look a bit like that. That's the prediction. And the problem with curving graphs is that there are loads of graphs that curve just like that. And so identifying exactly what the curving graph is going to be difficult. And then digging H out of it is going to be even harder. Do you remember the trick that we use sometimes when drawing graphs to get away from this curve isn't a good way to dig a constant out? Do you remember the trick that we use? I think we've done it. I think we've done it. Maybe we haven't, but do you know a trick? Or make up a trick.
You could sort of like make it a straight line.
Yeah, we want to make it a straight line. We love straight lines because there's no ambiguity about a straight line. A straight line is straight. What is the mathematical equation for a straight line, just in terms of y's and x's?
Y equals mx.
Yeah, y equals mx. Y equals mx. So, plus c, of course. But what we're going to do is, if we plot v on the y-axis, and not lambda, if we plot 1 over lambda on the x-axis, then the prediction is that we will get a straight line. Y equals mx plus c. We will get a straight line that passes through the origin because there's no intercept, and it will have gradient hc over e. That's the prediction. So if we don't plot lambda there, we plot 1 over lambda there, we should get a straight line, and its gradient should be hc over e. That is the prediction. So we just need to check if our data works. So you currently have this in your book. What you need to do is add yourself an extra column, left or right, nobody cares, for 1 over lambda. So you need to get your calculator out, and you need to do 1 divided by lambda to give you your values. And then you're not going to plot this column, you're going to plot these 2 columns. This on your y-axis, this on your x-axis, draw in a line of best fit, and then scoop the gradient out of it. Now, I suggest you just leap in and do that. What is likely to happen is that you're going to get power of 10 errors. So your V's are going to be fine, but your lambda's got a nanometers in it. So if I were you, this is in 10 to the minus 9 of a meter. When you convert it, it'll just be in 10 to the 9 meters. So your scale on your y-axis will be volts. Your scale on your x-axis will be 10 to the 9 meters rather than meters. Oh, meters to the minus 1. And we'll work out the powers of 10 when we do the gradient later. So you're going to need some graph paper to plot your, 5 points on. And so I've put some on the chat. So if you've got a printer, print it. If you haven't got a printer, you can open up Excel or Sheets, and you can use that to plot yourself a graph. And then when you have plotted yourself a graph, I need you to put a line of best fit on it. Then when you've got a line of best fit, I need you to stick a triangle on it. And I need you to work out the gradient. And I need you to come back to class in tomorrow's lesson with a gradient. We've got, 15 minutes left today, so we're not going to have time to go through it today. So come back to class tomorrow with the gradient of your graph. Right, there are just 2 little things that I want to ask you to be careful about when you do this. The first is, seeing as I just mentioned it, this triangle, when you draw it, could you please try to make your triangle as big as possible? You should be using at least half of your line of best fit to make sure that when you work out this difference, any tiny little errors you make in reading the endpoints are very, very small compared to the size of the interval itself. So always make sure that that is much, much bigger than any tiny little error you're making reading at the end of it using the scale of the graph. And on that subject, you can make your life a lot easier as well by using as much graph paper as you possibly can so that you aren't having to fiddle around with a tiny little scale on this axis. The second thing that I want you to be careful about is we are expecting the straight line and we are expecting it to pass through zero. That's two different expectations. And it might be possible to have one without the other if errors have crept in. So a common thing that happens when doing this experiment is that the line is, well, you can, on 5 points, it's difficult to be sure, isn't it? I've only got the 5 LEDs, but it's possible to convince yourself it would be straight. But hand on heart, that straight line that you pick might miss zero slightly. When you miss zero, we start looking for zero errors rather than forcing the line to go through zero and have a slightly incorrect gradient. If it is a well-defined straight line with a well-defined gradient, and then you artificially change that gradient to force it to go through zero, given that it's the gradient that we are very interested in to measure h, you're going to completely ruin your experiment. So I don't know if this data will generate a line that goes through zero or not, but if it doesn't go through zero, allow it to not go through zero, and then we'll discuss sources of a zero error next time. Why might our zero not be where we think zero is, basically? So I don't know how it will work out, but I guess you'll find out. Come tomorrow, please, with a finished gradient, if you can. And if you can figure out your powers of 10, even better. You're looking for a -34, aren't you? Okay, any questions? How do you graph on sheets? Does it not have, like Excel, does it not have an insert scatter graph function? So you make a table, so put in your wavelength data, put in your V data, put a formula in here for equals 1 over that, and fill it down, and then highlight that column, and go to the insert menu, and you want to insert a scatter graph, not a line graph, a scatter graph. And then actually on that point, if you do it electronically, I want you putting the line of best fit on yourself potentially. It's okay, actually, if you tell it to add a trend line that's linear, they're pretty good at adding a linear trend line. It's curving ones that they're rubbish at, but you can probably tell it to add a linear trend line. And then certainly on Excel, I presume Sheets is the same. You can tell it to display the trend line, the equation for the trend line, and then you'll be able to see it in y equals mx plus c format. So actually, you'll be able to pull the m off from the software when it prints the equation. But if possible, print it out, draw your own line of best fit by hand, and put your own triangle on and do it by hand, because those are the skills that you're practicing more so than learning how to get the software to do it for you. Okay, you've got a quarter of an hour left of this lesson. Have a go. I'm going to leave the meet running. So if you get stuck or you're unsure, you can ask me, but you're welcome to leave the meet if you want to. It's entirely up to you. Is that right?
Thanks, sir.
Thanks, Laura.
See ya.